In this video, let's see the importance of network function. In order to discuss that one, first of all, let's see what is port in a network. Detailed discussion regarding port, that is two-port network, is coming in 5th module. Any network may be diagrammatically represented by a rectangular box like this. To connect a network with another network, two terminals must need to come from that rectangular box, which is representing a network. This two-terminal network is called one-port network. Or in other words, if a network having one pair of terminal, then that network is termed as one-port network. Thus, a one-port network contains only one pair of terminals. Let's consider a network like this. Here two terminals are there. This can be represented by a rectangular box with two terminals. Here this network contains only one pair of terminals. So this is a one-port network. So this is the schematic representation of one-port network. Similar way, if a network contains two pair of terminals, then that network is said to be two-port network. Here first pair, that is one pair of terminal, is input port. It is termed as input port, and another pair of terminal being output port. Let's consider this network. It contains input terminals like this A dash and output terminals like this B dash. We can represent this network by a black box or rectangular box with two pair of terminals in each side. Let this pair of terminal be represented by 1 dash. It is termed as input port, and this pair of terminals 2 dash can be considered as output port. So this is the representation of two-port network. So a two-port network is a network in which it has two pair of terminals. Pair means two, so totally it contains 4 terminals. Now let's see what is network function. A network exhibits the relationship between transform of excitation, that is source, to transform of response in an electrical network. Examples are driving point impedance, driving point admittance, and transfer function. Now let's see driving point impedance and admittance corresponding to one-port network. Here one pair of terminal is available. Across this we are giving voltage source so that a current I of t is flowing through this network. When we are transforming this voltage into S domain, it becomes V of S, and corresponding transformed current is I of S. Now driving point impedance is defined as the ratio of transformed voltage to transformed current. Transformed voltage is V of S and transformed current is I of S. And corresponding to admittance, it is the reciprocal of Zs. Y of S is equal to I of S divided by V of S, that is known as driving point admittance Y of S. Considering two-port network, it contains two pair of terminals, that is input pair and output pair. Say the input voltage is V1 of S and input port current is I1 of S. And similarly, corresponding to second port, the voltage is say V2 of S and current be I2 of S. So the driving point impedance at port 1 dash, that is input port, is Z11 of S is equal to this voltage, that is transformed voltage to transformed current V1 of S divided by I1 of S. Say this is 1 dash and this is 2 dash. So corresponding to 1 dash port, that is input port, driving point admittance is Y11 S, which is equal to reciprocal of Z11 S, that is I1 of S divided by V1 of S. Similarly, driving point impedance at port 2 dash is Z22 of S, which is equal to transformed voltage to transformed current, that ratio V2 of Es divided by I2 of Es. and corresponding to that one, driving point admittance is obtained as Y22 of S is equal to I2 of S divided by V2 of S. Now let's see transfer function. The relation between transformed voltage or current in one port to the voltage or current at the other port is called transfer function. In that, we can have voltage transfer function, current transfer function. Voltage transfer function is represented by G of S. It may be G12 or G21. The ratio of transformed voltage at one port to transformed voltage at the other port is known as voltage transfer function G of S. When we are considering this one G21 of S, it is the ratio of V2 of S to V1 of S. That is transformed voltage at second port to transformed voltage at first port. Similarly, G12 of S is equal to the ratio of transformed voltage at first port to transformed voltage at the second port. Similarly, we can have current transfer function ratio or simply current transfer function. It is represented by alpha of S. It may be alpha 12 of S or alpha 21 of S. It is the ratio of transformed current at one port to transformed current at another port. If we are considering this one alpha 12 of S, it is the ratio of transformed current in first port to transformed current in second port. Similarly, alpha 21 of S is equal to transformed current in second port to transformed current in first port. So far we discussed about transfer function, voltage transfer function and current transfer function. Here it is the ratio of voltage to voltage in two ports, that is voltage in one port to voltage in second port, or current in one port to current in another port. Now let's see the transfer impedance and admittance. It is the ratio of voltage in one port to current in another port, or current in one port to voltage in another port. First of all, let's see transfer impedance. It is the ratio of transformed voltage at one port to transformed current at other port. It may be Z21 of S or Z12 of S. Z21 of S is defined as the ratio of transformed voltage at second port to transformed current at first port. Similarly, Z12 of S is the ratio of transformed voltage at first port to transformed current at second port. Similar way, transfer admittance is the ratio of transformed current at one port to transformed voltage at other port. Y21 of S is equal to I2 of S divided by V1 of S, and similarly Y12 of S is equal to I1 of S to V2 of S.